What if I told you your low-risk portfolio strategy might actually just be underinvested? Minimum variance portfolios, for example, often look good on paper. Smoother returns, smaller drawdowns, but there's a catch. They're taking less risk. We saw exactly that in the last video. We looked at equal weighting and minimum variance weighting multi-asset portfolios. We saw that even though we highly underperformed with our min-var portfolio, it had similar Sharpe ratios with way reduced volatilities. But what now happens if we make the playing field level? In this video, we're not just comparing strategies, we are comparing them correctly. We are going to use leverage to scale a minimum variance portfolio to the same risk level as an equal weight portfolio. We can then see that we now all of a sudden get similar returns. We do all of this in Python, and this is exactly what we do at Code and Capital. Rigorous research, practical implementations, and institutional quality portfolio thinking. No shortcuts, no misleading backtest, just clean, risk-adjusted insights. Because once you normalize risk, the difference you're left with is real alpha, or, on the other hand, the lack of it. Let's break it down step by step. At first glance, minimum variance portfolios often look good on paper with high Sharpe ratios. We saw that in the last video where we compared our multi-asset portfolio on an equal weighting and a min-var weighting. We saw that the Sharpe ratios for both almost aligned, while the min-var portfolio had a quarter of the daily volatility. In general, min-var portfolios are smoother, they have smaller drawdowns, and just feel more stable. But here's the issue. There's structurally lower risk. So when you compare a minimum variance portfolio to something like an equal weight portfolio, you're not actually comparing strategies. You're just comparing different levels of risk exposure. Lower volatility naturally leads to lower expected returns, whereas higher volatility comes normally with higher expected returns. So of course, the profiles will look different because they're playing complete different games in the end. This is not an apples to apples comparison, you could say. It's like comparing a conservative bond portfolio, which is mainly what is in the min-var portfolio, to an equity portfolio, and you ask the question on which one is better. So what are we gonna do instead? We normalize the risk across the two portfolios. We scale the minimum variance portfolio so that its volatility matches the benchmark, in this case the equal weight portfolio. Now both strategies are taking the same amount of risk, and we can just ask the question on which one uses this risk more efficiently. Because once the risk is aligned, any differences in the performance is no longer about the exposure, it's about the true alpha of the strategy. So how do we actually align the risk? We apply leverage to the minimum variance portfolio. And this is a critical point. We're not just making the strategy riskier for the sake of it, we are scaling the exposure in a controlled way, so that both portfolios in the end align at the volatility level. The way we do this is straightforward. We take the ratio of target volatility to the strategy's volatility and use that as a scaling factor on portfolio weights. That's exactly the formula that you see on screen here right now. That means in the end that metrics like Sharpe ratios, drawdowns, and return path are actually comparable between the strategies. And more importantly, this separates two things that are often mixed together: risk-taking and skill. Because before scaling, a strategy can look better simply because it takes less risk. And after scaling, that excuse is normally gone. And what you're left with, the only thing that really matters in the end, is how efficiently does this strategy convert risk into return? And in other words, true alpha. Now a lot of people assume that leverage is linear. So if you double your exposure, you just double your returns. But that's actually not true. Leveraged returns are nonlinear. So in other words, your levered return is not just leverage times return, because there's two main reasons for it. The first one being compounding, and the other one is volatility drag. we can look into that in an example. So let's say your strategy, you start on $100 and your strategy goes up 10%. All of a sudden you have $110. Now if you lose 10%, it goes 100 times 0.9, so you're back to $99. So you're effectively 1% down or $1 down. If we do the same exercise with a 2% leverage, your strategy actually now goes up 20%. So $100 become $120. But now instead of going down 10%, because you're 2 times levered, it goes down 20%. So all of a sudden you're back to $96 instead of $99. So you're now down 4%, whereas if you just scale returns, you would only be down 2%. So the loss is a little bit larger here. So when we scale strategies using leverage, we're not just increasing returns, we're also introducing path dependency and potential performance drags, which means leverage needs to be handled carefully, especially in volatile strategies. Let's check next what that would look like in code. I already loaded in the price series of the 4 strategies that we looked into in the last video, being our equal weight and our min var, and I made them returns. So we can see that we have our equal weight returns over time and our min var constraint returns over time for our multi-asset strategies. What we want to do now is we want to create our leverage returns, our leverage series over time. So first we want to create a window being, let's say, a 1 year look back. We can just say that our realized vol is returns dot rolling, and we can look at window equals window, and min periods we also want to make sure that we have enough look back to create a meaningful standard deviation, and then we just take the standard deviation and we annualize that one. So we do np dot square root of 252. So that now, if we look at realized vol, is our rolling realized volatility. And here we can see exactly what we talked about in the last video, that the equal weight volatility is almost 3 times as big as the min var constraint volatility. So if we now say, all we have to do is create the formula that we had on screen earlier. So we say our target leverage equals, and then we can just say, we say realized vol on equal weight divided by realized vol on min var constraint. So if we look at the target vol, we now see we have a nice vol or a nice leverage over time where we see our almost 3x here. And now all we have to do is make it a little nicer to use. So we say target leverage equals target leverage dot to frame. We call it name equals min var target leverage, and we drop our NAs that we have in the beginning, and we now have a nice data frame. We can look at that in a plot form too, where we have our leverage over time now, and we can see it spikes all the way up to almost a 4x leverage that we need to align the risk for our min var strategy with the equal weight strategies. Next, we will put that into an actual backtest. So we lever up our min var portfolio to match the equal weight, and we will see what that does to our performance. So far, we've used leverage as a tool to normalize risk. But in practice, leverage doesn't exist in isolation. It's implemented through margin. Margin is essentially borrowing capital to increase your exposure. It allows you to take positions that are larger than your actual equity. Leverage describes how much exposure you have relative to your capital, but margin is the mechanism that determines how much leverage you can actually take. And this is where things get real. Leverage is not free. Once you use margin, you're paying financial costs. Whether that's a funding rate, a spread, or some broker-specific charge. On top of that, margin comes with constraints. If your portfolio moves against you and you breach margin requirements, positions can be forcibly liquidated. That's called a margin call. So margin doesn't just enable leverage, it limits it, prices it, and can even force you out of the market at the worst possible time. Which means any strategy that relies on leverage has to be evaluated after financing costs and under realistic margin constraints. Because in the end, the edge only exists if it survives funding. So let's go back to our Code and Capital backtesting engine and see how we implement the margin leverage strategy in code. As previously in the other videos, we already implemented the equal weight and the min-var strategies. We go back to the bounded min-var strategy here. Now all we have to do is we want to lever up the position using our target leverage. So we have to scale our weights by our leverage factor at each point in time. It is very important here that you don't introduce look-ahead bias, so you want to take the leverage factor as of the day prior, which is already implemented into the backtesting engine. You then have to allow on how much margin your strategy is allowed to take. As this is a dummy backtest here, we just set it so we can always reach our max margin here, our max leverage that we want to take. So we set our margin to 6. If we run the backtest, we can then see that now after our leverage is applied, all of a sudden the min-var levered version almost matches the returns of our equal weight strategy. We can look into the weights and we see our leverage in full work here by having positions or having a portfolio weight of around 400% at its peak. You can now see that we, for example, take a 86% position in the US dollar or a 96% position in treasury bonds. Looking at the stats here, we now see that our total return almost is times 5 now compared to our default min-var strategy. We went from 0.5 to 2.7, which almost now matches the equal weight annualized returns. Our Sharpe ratio stays high and is still comparable to the equal weight strategy. So far, we have not accounted for transaction cost though. What we have up here is just a non-transaction cost version of what happens if we lever up our position times around 3x all the time. We can now implement transaction costs. In our example here, we take the Fed funds rate that we pull out of Fred. We already published a video on how to pull Fred data in a reliable pipeline. So if we look at the Fed funds rate, we can see it over time. We know that around 2020 to 2022, there was not a lot of funding costs that we had to pay, but now it's spiked back up to around 5% and sits at around 3.5% right now. As I mentioned before, we have a video on how to pull that data into your quant pipeline already. If we impose that pipeline, if we impose those fees now, we can see I put that into our margin class here by saying our financing rate matches the Fed funds divided by 100 because we don't want it to be 400%, we want it to be 4%. So now looking at that graph, we all of a sudden see that our min-var levered financing strategy lags a little bit behind because we have to pay those around 4% on our capital that we take from the bank in the end. We still outperform the default min-var strategy. We just have to be very careful on how we test the strategy, and because we can't just lever up our position times 5 without accounting for transaction costs. So what we've done here is take a minimum variance strategy and evaluate it the way it would actually be used in practice. We didn't just compare raw returns, we normalized risk using leverage and tested the strategy in a realistic setting using Python. Because once you control for risk, you can finally see what's real and what's just a function of lower exposure. That's where the difference between a good looking backtest is and actual delivering alpha. And that's exactly what we are trying to do at Code and Capital. Rigorous research, practical implementation, and institutional quality portfolio thinking. If you want to go deeper, check out the full research and code on codeandcapital.com. And if you found this useful, subscribe. We break down quantitative strategies the way they actually used. Because in the end, it's not about the strategy that looks best, it's about the one that holds up under real conditions. I will see you at the next one.